just an example of how we approach the testing of some silicon carbide high voltage diodes. And then at the end I have a few slides about some tests we performed also onto silicon carbide power MOSFETs. Well, these tests were performed in the frame of a couple of ESA contracts, and the problem was since a few years ago it was discovered a high sensitivity of these devices to heavy ions. Silicon carbide is a very promising technology because of it has a lot of advantages, extended temperature range, good electrical performance, but well, it is also immune to TID and protons, but this problem with heavy ions is quite destructive. Well, these are the points of the presentation. I'll start showing just the problem, then explaining the test approach we used to test this phenomenon that is not very well understood, and then explain the steps we follow in order to try to understand the dependency of the degradation with LET and the different reverse biases we apply to the diodes. We will try to end in a safe operating area because maybe you have to use these diodes anyway, so you need to know up to which voltage and LET you can use the devices. And at last, the summary of the testing on the power MOSFETs. Well, this is the problem description. You have a silicon carbide high voltage diode biased in reverse under a heavy ions beam. In this case, we have an LET of 10 MeVs milligram square centimeter and the flux of 100 ions per square centimeter and second. In fact, the device is completely stable when it is biased at 100 volts and 300 volts in reverse. But just at the very moment that the beam is activated, when the device is biased at 500 volts, you have catastrophic damage of the device, that it's not a diode anymore. Well, as I said, this phenomenon is not very well understood, and the outcome of this test could be helpful for the manufacturers to improve the device sensitivity. We tried to test as many devices as possible, different part types, and in order to see if any one of them showed better behavior from the others. But always keeping in mind that you have a test approach, but you don't have information on where the devices are going to fail, so you have to perform several steps strategy to allocate the critical values, and then maybe distinguish between devices the behavior. Maybe the quality of the raw material or the geometry of the devices is better. Any one is better than the other one. Well, this is not a pass-fail radiation test because we know the devices are going to fail. We want to extract the maximum information. And we need flexibility because a very raw initial approach can lead to no information at all if you damage all the devices without control. Well, again, we try to define a safe operating range for the devices in order to use them. Well, this leads to several phases approach, and we have defined the three phases. Phase one, it's the critical LET and bias value allocation. We perform this phase onto the different part types, performing HE at each LET different voltage steps, but very wide voltage steps, because we didn't know where the devices were going to fail. So this is only allocating the problem. The phase 2 is degradation characterization. Then we go where we expect to have the degradation, but not completely, let's say, catastrophic instantaneous degradation or damage, but in order to study how that depends on the LET and the bias voltage. And then the phase 3, we go where we don't expect to have the damage, and we accumulate some fluence in order to demonstrate that the device is not sensitive at that combination of LET and bias. Okay, well, this has been explained in some presentations yesterday. In order to perform the heavy ions test, you have to remove the lid of the device, and also the coating gels that these high voltage devices might have. We also want to test the heavy ions under high voltage biases. So that gel on top of the die was there for a reason, to isolate. So if you remove it, you can have discharges and damage the device without any heavy ions needed. So we use a perylene C coating of the devices. You can grow a perylene coating of 15 microns we use to use, and this very thin coating allows the heavy ions to reach the active area of the device and completely solve the problem of the discharges. Well, you have to check the devices before and after the perylene coating in order to ensure everything is stable before the test. Well, general considerations about this test is, okay, you need to test a lot of devices and a lot of conditions in the 3 phases, so you have to try to minimize the beam time that leads to a high cost. So we have a picture of a custom test board we designed in order to test 8 devices per board in Louvain and UCL facilities, so you don't have to open the chamber and lose a lot of time in changing the samples, but you have to test with high voltage and take into account some considerations. You need also to think about the LETs you're going to use, because changing from an LET to the next one can take a lot of time, and that is beam time. Okay, this is the phase 1 initial approach. I say initial because we initially proposed these bias steps up to 900 volts, but as you will see in the next slide, if you have completely destroyed the device, you stop, and you don't achieve these values. We start with a fixed small LET value, and then we present this wide steps of voltage. We used these 4 ions in order to have these LETs, and we also performed some tests tilting the devices, but only to know, but we observed that even increasing LET because of the tilting, you reduce the cross section of the damaging caused by the heavy ions. So we will take that note into account, and we will. You don't know if the tilting is going to follow the cosine law or not. Okay, this is the same graph I showed at the beginning, but a bit explained. We performed several beam steps while increasing the reverse voltage, and we plot the reverse current during all the tests. So we don't raise the reverse voltage from a step to the next one with the beam on, because otherwise, if the device is damaged, we wouldn't know if it's just the electric field or because the device was a bit damaged or something. So we wait for a few seconds and then turn on the beam. So here you have, just starting the beam, you have the damage, and this current is the setup current, setup limited current. Well, we never arrived to the 700 bias step. This is performed with using all the part types we have. So you have an idea or where you have a completely destructive damage of each part type. In phase 2, we adjust the LET to a couple of values, higher values than